Welcome back to the second lecture in Module 3, Finite Difference Method. In the first lecture we covered basic methodology of finite difference. This lecture we are going to focus on obtaining finite difference approximation of first order derivatives, and thereafter we will go to obtain approximation for second order derivatives, and followed by approximation for multidimensional derivatives and applications to scalar transport. Let us have a brief recap of what we did in the last lecture. We discussed basic features of finite difference method. What are the features which make it very attractive for CFD applications? And then we described the conceptual framework of obtaining finite difference solution for a flow problem. And we discussed the basic conventions or notations which we use for representing finite difference grid points and functions. And we reiterated the basic concept behind finite difference approximation, which is based on the basic definition of a derivative. So in this lecture we would now focus on, we continue from there, and we would obtain the finite difference approximation of first order derivatives. The outline of this lecture: we will first have a recap of the approximation approaches which can be used to obtain the finite difference approximation of partial derivatives, and then we would focus on approximations based on Taylor series expansion. In particular, we will look at a general procedure for obtaining finite difference approximation for first order derivative on uniform grids, and then we will have a look at a generic method called polynomial fitting method to obtain an expression of finite difference approximation of first order derivative. Now, we have already seen that most popular approaches, Taylor series expression, polynomial fitting, Paré approximation, difference equation. There are a few other approaches. We would focus primarily on Taylor series expansion and polynomial fitting. So now let us have a look at what is Taylor series expansion. Suppose we are dealing with a continuously differentiable function f(x) defined on the real line. So f(x) can be expanded in Taylor series about x is equal to xi as f of xi is equal to value function at point xi plus x minus xi, the first derivative of f at point xi, plus x minus xi square divided by factorial 2, and the second derivative of f at point xi plus other derivatives plus the nth term x minus xi to the power n divided by factorial n, nth derivative of f at point xi plus higher order terms. Now let us use this Taylor series expansion to obtain different expressions or different approximations for first order derivative. This is a summary slide. We will come back to it after we had finished the derivations. So let us do the formal derivation. So we are interested in finding out approximations for first order derivatives based on the Taylor series expansion. So let us rewrite what we just saw in the previous slide. So Taylor series expansion about x is equal to xi. So at point x in the neighborhood of our grid point xi, the value function can be expressed in terms of the function value at the grid point I, that is f of xi, plus x minus xi del f over del x at point xi plus x minus xi squared divided by 2 factorial second derivative of f at point xi plus x minus xi cube divided by 3 factorial the third derivative plus so on. So, we can express the remainder terms by symbol h, where h refers to our higher order terms. Okay. So, now let us draw our one dimensional grid. We are at point xi. We have got one node to the right of xi, which we will call it as xi plus 1. The indices of these nodes are I plus 1, and then the grid point to the left of xi, that is xi minus 1, and its index is I minus 1. Now, we can write the function values at the two neighboring points in terms of the Taylor series expansion. So, let us use the value of function at point x is equal to xi plus 1. Function f at xi plus 1. So, now let us switch over to our shorthand notation, that is fi plus 1, which stands for f of xi plus 1. This would be equal to f of I. We have now used fi for f of xi. So, let us just have a recap of the shorthand notations which we have introduced earlier. This fi stands for f of xi. Fi plus 1, we would use this in place of function value at the node xi plus 1 and so on. Okay. So, now fi plus 1 is equal to fi plus x of I plus 1 minus xi into del f over del x at the grid point I plus x minus xi plus 1 minus xi whole squared divided by 2 del 2f over del x squared xi plus or higher order terms. Now, these differences xi plus 1 and x minus xi we can write in terms of our delta symbols. So, we can write in a compact form that fi plus 1 is fi plus delta xi, where remember we have used the symbol delta xi to denote the difference between xi plus 1 minus xi. So, fi plus 1 it becomes fi plus delta xi del f over del x at I plus delta xi squared divided by 2 del 2f over del x square at point I plus delta xi cube divided by 6 del qf over del x cube plus our higher order terms. So, this is function value at point xi plus 1 in terms of the function value at node xi and the difference between two node points, the distance delta xi. Let us call this equation 1. Now, we can straightway get a difference approximation by just transferring the fi terms on one side. So, this gives us our first expression for del f over del xi, del x at point I. This is f of I plus 1 minus fi divided by delta xi minus delta xi by 2 del 2f over del x squared at I minus delta xi cube delta xi square by 6 del qf over del x cube plus higher order terms. So, we can retain the first term on the right hand side as our approximation. So, we can write an approximation for first order derivative at node I as f of I plus 1 minus fi divided by delta xi, and the remaining terms they become what we call as our truncation error. So, if you look carefully, this truncation error is of order delta xi, and here we have used the value at the node forward or to the right of point xi. So, this is our celebrated forward difference approximation. Next, what we can do is to use the function value at the left node, and that will give us what we call as our backward difference approximation. So, this fi minus 1, which stands for the function value at point xi minus 1. This can be expressed by our Taylor series as f of I plus x of I minus 1 minus xi del f over del x at I plus x of I minus 1 minus xi squared divided by 2 factorial, the second derivative del 2f over del x square at point I plus higher order terms. Let us write it more compactly by introducing our delta x terms. So, remember that delta xi minus 1, this is xi minus xi minus 1. So, in terms, if you introduce this delta symbol, we get f of I minus 1 is equal to fi minus delta of xi minus 1 del f over del xi plus delta xi minus 1 squared del 2f over del x squared at I minus delta xi minus 1 cube divided by 6 del cube f over del x cube point I plus higher order terms. So, if we rearrange this equation, that will give us the value of the derivative at point I, or rather approximation for that. So, del f over del x I, this can now be written as fi minus f of I minus 1 divided by delta xi minus 1 plus delta xi minus 1 square divided by 2 del 2f over del x squared at point I minus delta xi minus 1 cube divided by 6 del cube f over del x cube at I plus higher order terms. So, we can retain this first term on the right hand side for our approximation of the derivative, and remaining terms they will become what we call our truncation error. So, we straightway get our BDS approximate scheme, backward difference scheme, del f over del x at grid point I can be approximated in terms of f I minus f of I minus 1 divided by delta x I minus 1. And once again what we can say is this truncation error for this scheme, this is of the order of delta x I minus 1. So, both forward difference and backward difference approximations, they give us a scheme of first order. Now, we can also obtain what we refer to as a central difference approximation. Now, the central difference approximation can be obtained by combining the two expansions which we had written earlier, one on the previous page which we wrote as an expansion at point xi plus 1, and the second one which we wrote as Taylor series expansion at point xi minus 1. So, let us subtract the equation 1 from 2. So, what do we get? F of I plus 1 minus f of I minus 1, f I gets cancelled, and we get delta x I plus delta x I plus 1 into delta f over delta x at I plus delta x I square minus delta x I minus 1 square divided by 2 del 2 f over del x square at I plus delta x I cube plus delta x I minus 1 cube divided by 6 del cube f over del x cube at point I plus remaining higher order terms. Now, this can be rearranged to yield the value of the first derivative. So, del f over del x I, this is equal to f of I plus 1 minus f of I minus 1 divided by delta x I plus delta x I minus 1 plus delta x I minus delta x I minus 1 divided by 2 del 2 f over del x square at I plus delta x I cube plus delta x I minus 1 cube divided by delta x I plus delta of x I minus 1 del cube f over del x cube at point I plus higher order terms. So, now let us retain the first x term on the right hand side as the approximation of our derivative. The remaining terms that is the one which we just put in curly braces, they represent our truncation error. So, we get the CDS approximation or central difference approximation for first order derivative as del f over del x I is equal to f of I plus 1 minus f of I minus 1 divided by delta x I plus delta x I minus 1. So, this is the approximation which we get. Now, truncation error is in this case, this is of the order of delta x I minus delta x I minus 1. So, formally the truncation error for the series on a non-uniform grid is still of order 1, but if you say it is a difference of 2 grid spacings. So, this truncation error for the series TE series, this will always be less than TE of a truncation error of forward difference scheme or backward difference scheme. Moreover, if you have uniform grid, then what happens on uniform grid, this the leading term in truncation error vanishes. So, for on uniform grid, TE series, this now becomes of the order of delta x square. So, that is why we say that look, the second order accurate, our central difference scheme is second order accurate. So, now let us go back to our slide and say the summary of what we just derived. So, we derived a forward difference approximation del f over del xi is equal to f of I plus 1 minus fi divided by this xi plus 1 minus xi, which stands for delta xi, and truncation error is of the order of delta x. Backward difference scheme by using values at the point left to our current point. So, del f over del xi is approximately equal to fi minus fi minus 1 divided by xi minus xi minus 1. Truncation error is still of the order x. So, both of these schemes, they are first order accurate. Next, we had obtained an expression for central difference scheme series del f over del x at I is equal to fi plus 1 minus fi minus 1 divided by xi plus 1 minus xi minus 1. This is what we get when we expand the terms delta xi plus delta xi minus 1, and this scheme is formally first order accurate. It is order of delta x on a non-uniform mesh, but has a much smaller error coefficient or truncation error value compared to our forward difference truncation error or backward difference truncation error. And if our mesh spacing were uniform, we get a very simple expression for the derivative del f over del xi is equal to fi plus 1 minus fi minus 1 divided by 2 delta x, and in this case truncation error is of order delta x square, that is to say our difference approximation is second order accurate on a uniform mesh. It is also possible for us to derive a central difference formula for first order derivative, which would be second order accurate on any grid, and for that we have to do a bit more jugglery or algebra with respect to the two expansions or Taylor series expansions which we wrote earlier. So, now let us derive a second order accurate central difference approximation or CDS on non-uniform grid. For this, you would rewrite our previous Taylor series expansions by dividing by the square of the mesh spacing. Our main purpose would be to eliminate the second order derivative from the expansions. So, let us write our Taylor expansion around Taylor expansion for x is equal to xi plus 1. So, this we can write as fi plus 1 divided by delta xi squared. We are just dividing the entire expression which we have written earlier by delta xi square. So, this will become fi divided by delta xi square plus 1 over delta xi del f over del x at point I plus 1 by 2 del 2 f over del x square at point I plus delta xi divided by 6 del q f over del x cube at point I plus our higher order terms. Similarly, let us rewrite our Taylor series expansion. Expansion for value at x is equal to x of I minus 1 in terms of a misspacing, and we can write this as f of I minus 1 divided by delta x I minus 1 squared. So, is equal to f I divided by delta x I minus 1 squared minus 1 over delta x I minus 1 del f over del x at point xi plus half del 2 f over del x square at I plus delta x I minus 1 divided by 6 del cube f over del x cube I plus higher order terms. Now, if we subtract the bottom equation from the top one, we would be able to eliminate the second order derivative. That is what we wanted. Let us call the first equation, top equation as 1 and the bottom equation as 2. So, subtract 2 from equation 1. So, what do we get on LHS? We will have f of I plus 1 divided by delta xi squared minus f of I minus 1 divided by delta xi minus 1 squared. On the right hand side, the first term would be, let us take fi common. So, 1 by delta xi squared minus 1 over delta xi minus 1 squared multiplied by fi. Similarly, for the second terms, let us take our del f over del xi common. So, del f over del x at point I, and we are left with 1 over delta xi plus 1 over delta xi minus 1. Sorry, there is a small correction here, this term has to be negative. The third terms they cancel, del 2 f over del x square, half of it is in top equation and the same in the bottom equation. So, these two would cancel out. So, the next term which we get is del cube f over del x cube at I delta xi plus delta of x I minus 1 divided by 6 plus higher order terms. Now let us simplify the terms a little bit. So on the left hand side we will have f of I plus 1 delta x I minus 1 squared minus f of I minus 1 delta x I squared divided by delta x I square delta x I minus 1 squared. On the right hand side similarly we will get delta x I minus 1 squared minus delta x I squared divided by delta x I square into delta x I minus 1 square. This becomes our multiplier for f I plus delta x I minus 1 plus delta x I divided by delta x I minus 1 into del f over del x at I plus del x I plus del x I minus 1 divided by 6. This is multiplied by the third order derivative del cube f over del x cube at I plus higher order terms. So now we can rearrange to obtain an expression for a first order derivative. So del f over del x at point I. So this would be equal to f of I plus 1 delta x I minus 1 square minus f of I minus 1 delta x I squared plus delta x I square minus delta x I minus 1 squared, whole thing divided by delta x I minus 1 into delta x I plus delta x I minus 1 minus delta x I minus 1 divided by 6 del cube f over del x cube at point I plus higher order terms. So now you can clearly say that we have by eliminating the second derivative del 2f by del x cube, we now get one CDS approximation by retaining the first term, which would be second order accurate irrespective of the grid spacing. So thus we can write our CDS approximation as and our truncation error this is of the order of delta x into delta x I minus 1. That is, this scheme is second order accurate irrespective of the mesh spacing. If a mesh is uniform, you can do a simple algebra. So, that I would leave as an exercise to you. So, exercise, so that above formula simplifies to standard series, standard delta x square accurate series for uniform grid. Now, so far what we did, we wrote a Taylor series expansion and we used our own ingenuity to eliminate few terms and obtain the difference approximation for the first order derivative. Now, the procedure was intuitive. So, we had to guess which equation to subtract and which one to multiply by what, and then do the subtraction. Now, if you are dealing with uniform grid, Chung proposed a general formula that if you have got uniform grid, difference approximation for first order derivative can be expressed by this simple generalized formula. Yet remember, for a uniform grid, on the denominator we will have this delta x anyway, and the numerator will contain the function values at different grid points multiplied by some numerical multipliers. So, just using this simple logic, Chung has proposed this formula del f over del xi is approximately equal to a f I plus b of f I minus 1 plus c f I plus 1 plus d f I minus 2 plus e f I minus 2 or I plus 2 and so on. So, we can choose as many number of the neighboring grid points as we would like to have to derive or to obtain a difference approximation for the first order derivative. And to obtain the values for this a, b, c, d, these coefficients, they can be determined from Taylor series expansions for upstream nodes, that is our nodes I plus 1, I plus 2 so on, or downstream nodes I minus 1, I minus 2 and so on. So, one simple example of this 3-point backward difference formula, that if you want to use the values at 2 downstream nodes or backward nodes in addition to the function value at point xi. So, afi plus bfi minus 1 plus cfi minus 2 divided by delta x. This should give us a difference approximation to the first order derivative at del f over del xi. Now, let us try and get the values of these coefficients by performing a simple Taylor series expansion. So, 3-point BDS. So, we had written as del f over del x I, this is approximately equal to a f I plus b f I minus 1 plus c f I minus 2 divided by delta x. Now, please remember, our grid spacing is uniform, that is, say this is our point I, delta x to the left of it we have got the point I minus 1 and this point I minus 2, this is further at its distance delta x from the node x I minus 1. So, the function value at point xi minus 1, if you use Taylor series expansion, this would become fi minus delta x del f over del x at I plus delta x square divided by 2 del 2f over del x square at point I plus delta x cube divided by 3 factorial del cube f over del x cube at point xi and plus so on, remaining higher order terms. Similarly, the function value at the grid point I minus 2 in terms of Taylor series can be written as f I minus 2 is f of I minus 2 delta x, because f I minus 1 node, this is situated at the distance of twice of delta x left of point xi. So, 2 delta x times del f over del x at point I plus 2 delta x squared divided by 2 del 2f over del x square at I plus 2 delta x whole cube divided by 6 del cube f over del x cube xi plus so on. Now, let us substitute these expressions in our formula 1. So, let us call that as 1, the expression for f I minus 1 let us call it equation 2, and the expansion for f I minus 2 let us call as 3. So, substitute two and 3 in equation 1. So, if you do this substitution, what do we get? On left hand side we have got del f over del x at I. On the right hand side, what do we get? Let us take 1 by delta x common and let us collect the terms one by one. So, a f I that remains as such, b times f I minus delta x del f over del x at I plus delta x square divided by 2 del 2 f over del x square at I plus delta x cube divided by 6 del cube f over del x cube plus the higher order terms plus c times f I minus 2 delta x del f over del x of I plus 2 delta x square, 2 delta x whole square, that becomes 4 delta x square divided by 2. So, that gives us 2 delta x square del 2 f over del x square at I plus 8 delta x cube divided by 6 del cube f over del x cube of I. Now, let us collect the terms together. So, what do we get? The terms which correspond to the function values. So, we will get a f I plus b of f I plus c of f I divided by delta x minus b plus 2c del f over del x of I plus delta x by 2 into b plus 4c del 2f over del x square plus so on. So now let us compare the terms on left hand side and right hand side. On the left hand side we have got only del f by del x and its coefficient is 1. So the coefficient of fi on the right hand side, that must be 0. So comparing these coefficients of f, del f by del x and del 2f by del x square, what do we get? A plus b plus c is equal to 0 minus b plus 2c is equal to 1 and b plus 4c, this would be equal to 0. So now can we solve these three equations to get the values? So I would leave that as a simple exercise. So exercise, solve for a, b and c, and once we have obtained the values of a, b and c, we will get our expression for the first order derivative using our generalized expression on a uniform grid. So that is what we get. We should get a is equal to 3 by 2, b is equal to minus 2 and c is equal to half. So and therefore we get this 3-point backward difference formula, del f by del x I is equal to 3 of fi minus 4 of fi minus 1 plus f of I minus 2 divided by 2 delta x. And if you can substitute the values of a, b and c into the terms which are the coefficient of del cube f over del x cube, you will find out the truncation error of this scheme is of order delta x square, that is this 3-point backward difference formula is second order accurate. Now next let us move on to the approximation of derivatives by polynomial fitting. So if we have any generic continuous function, let us call this function fx, it can be approximated by a polynomial as, now we have taken the polynomial expansion around the point xi to simplify the algebra for obtaining a finite difference expressions. Fx can be written as a0 plus a1 times x minus xi plus a2 times x minus xi whole square plus and so on up to an x minus xi to the power n. Now these coefficients are a's, a0, a1, a2 and an, they can be obtained by fitting this interpolation curve to function values at appropriate number of points. And once we have obtained this approximation or this interpolation curve, how do we obtain the derivatives? That is very simple. Let us just differentiate this interpolation function. So if we differentiate it once, what do we get? Del f over del xi, that will simply be the coefficient a1. Differentiate it twice, so we get del 2f over del x square is equal to twice of a2. Similarly third derivative at point xi, this will become 6 times a3 and so on. So once we have obtained this interpolation, we should be able to obtain any order derivative up to order n minus 1 using this. As an example, let us find out using polynomial fitting a 3-point finite difference approximation, for which we would need a quadratic polynomial at grid points I minus 1, I and I plus 1. We want to have a quadratic polynomial fitting. So f of x, this would be approximated by the polynomial a0 plus a1 times x minus xi plus a2 times x minus xi whole square. So here we have got 3 unknown coefficients a0, a1 and a2. and these we would determine by using function values at point I minus 1 and I minus 2, or rather let us take a centralized difference formula. Let us use the values at I minus 1 and I plus 1. So, there are 3 node points. So, what is the function value at point xi? That is our fi. This would simply be equal to a0, because remainder terms, if we substitute x is equal to xi, they vanish. So, this becomes our first equation. F at xi plus 1, what will this be? We denote it by fi plus 1 is equal to a0 plus a1 times x of I plus 1 minus xi plus a2 times x of I plus 1 minus xi squared. Now, let us make use of our shorthand notation for the grid spacings. So, our xi plus 1 minus xi, we would use the symbol delta xi. So, therefore, we get an expression of this form a1 times delta xi plus a2 times delta xi squared is equal to fi plus 1 minus fi, where we have substituted the values for a0. a0 is equal to f of I. So, this becomes our second equation. Now, let us fit this polynomial at point I minus 1. So, fit the polynomial curve to the function fx at x is equal to xi minus 1, then what we will get? F of xi minus 1, which we would denote by f subscript I minus 1, is equal to a0 plus a1 times xi minus 1 minus xi plus a2 times xi minus 1 minus xi whole square. Introduce the grid spacing, delta notation. So, delta x I minus 1, this stands for xi minus x of I minus 1. So, in terms of this grid spacing, which is a positive quantity, the previous expression would be f of I minus 1 is equal to fi, substitute as fi the value of a0 minus a1 times delta xi minus 1 plus a2 times delta xi minus 1 whole square. So, if we rearrange, what do we get? We get a1 times delta xi minus 1 minus a2 times delta xi minus 1 whole squared is equal to fi minus f of I minus 1. So, this is our third equation. So, now we have got 3 equations for 3 unknowns 1, 2 and 3. The first equation straightway gives us the value of a0, We are interested in finding out the value of a1. So can we solve equation 2 and 3 to get the value of a1? There are two simple linear equations and it should be pretty straightforward to eliminate this a2. So how do we eliminate a2? Multiply equation 2 by delta xi minus 1 squared and equation 3 by delta xi. So what do you get? Equation 2 into delta xi minus 1 squared. So this will give us a1 times delta xi minus 1 squared plus a2 times delta xi square delta xi minus 1 whole square is equal to delta xi minus 1 square times f of I plus 1 minus f of I. Equation 3 times delta xi squared, that will give us a1 times delta xi squared delta xi minus 1 minus a2 times delta xi squared delta xi minus 1 squared is equal to delta xi squared fi minus f of I minus 1. Just add these two equations and thereby we would be able to eliminate a2. So we get a1 times delta xi minus 1 into delta xi minus 1 plus delta xi, and this is equal to delta xi minus 1 square f of I plus 1 minus fi times delta xi minus 1 squared plus fi times delta xi squared minus delta xi squared times f of I minus 1. So if we rearrange the terms, we straightway get the expression for a1, and this a1 is nothing but the derivative which we wanted, del f by del x at point I, or x is equal to xi, so we get this as delta x I minus 1 whole square f of I plus 1 minus delta xi squared f of I minus 1 plus delta xi square minus delta xi minus 1 whole square times fi divided by delta xi minus 1 delta xi minus 1 plus delta xi. So now we have obtained an expression for first order derivative using polynomial fitting, and if you want you can go back and compare. We have obtained same expression earlier using Taylor series expansion. So that confirms that the two approaches can give us identical results. So we can either use polynomial fitting approach or Taylor series expansions to obtain the expression for the first order derivative. And how about the accuracy? You can find out or work out the truncation error term by putting the Taylor series expansion, and this is a general observation that in general approximation of the first derivative possesses the truncation error of the same order. For instance, we just use a quadratic polynomial fitting which was second order polynomial, and the approximation which we got, that was second order accurate. So in general the approximation of the first derivative possesses a truncation error of the same order as the degree of polynomial used to approximate the function. So that is where we are going to start today, and the next lecture we will take up the finite difference approximations for second order derivatives.